And now Jonas will start his talk about the ALF Basics overview.
Yeah.
Okay, and I will let you start and go to the restroom. Then I'll be right back. Right.
Okay. Have fun.
It's not very polite.
So yeah, thank you. Yeah. Anyway, I'm gonna take a step back now, basically. So we now talked about PyAlf, but now I'm gonna go back to kind of ALF or vanilla ALF or what however want to call it. I'll move this to the side if it's somewhere else. Yeah, and so basically, in this talk, I will just give a brief overview over the source code in ALF, and like if people want to dig into the source code, this will be very helpful to just get an idea which files to look at and how Hamiltonians, like where the models are defined, interact with the actual code where all the Markov chain Monte Carlo is happening. So and this is like, yes.
The screen share is off.
Oh, how can I continue it? Ah, here. No. So thank you. Okay. Yeah. So this is like the first lecture on a series of talks about the basic building blocks, basically, of ALF, or basic building blocks of the models in ALF. So yeah, right after this talk, I will talk about the lattices, and then on Tuesday and Wednesday we have other talks about the observables, the interactions, and the hoppings, and then after that there will be a demonstration on how to build your own model out of these building blocks. And on Thursday, there will also be a talk about PyAlf. Yeah. So yeah, so basically have first I'm gonna talk a bit about the folders, like what the different contents of the folders where are the interesting things, and then briefly talk about the code structure. So how as I said, how the Monte Carlo core, the Markov, does the Markov chain Monte Carlo interacts with the Hamiltonians, which are most likely, like, which are the main thing touched by normal users. Yes. So this is like part of the folder structure. If you clone the ALF source code, you will see parts of this. So one interesting thing will be here the documentation doc.pdf, which is a very detailed documentation about all the like describes how to use ALF, how ALF works, and yeah, it's very detailed. So if you have some detailed questions about ALF, you might find your answers there, very likely. Then in this script and parameters files folder, there's the start folder, which is a sample folder of how to start an ALF simulation. So to start an ALF simulation, there are always two files needed: the parameters files and the seeds file. So the seeds file for a random number seed and the parameters file to give the parameters to simulate. And then to continue a run, you always, like, if you have a run in one simulation, I mean, this was already part of the discussion earlier. If you have a simulation and then you want to continue that simulation, then you have to rename, like, ALF does checkpointing and then creates these outconf file, and before resuming a run, you have to remove, like, you have to rename these outconf to inconf. Otherwise, you will basically repeat the same run again, and then everything you do will be wrong, basically. Yeah, and for this is the script. If you use PyAlf, you don't have to worry about this. This PyAlf will do this basically for you. Yeah, there's also this test suite file, which is a folder which contains a suite of unit tests. This is for most users not so interesting. And here's in this Mathematica folder is Mathematica notebooks to do which can be used for doing a Wick decomposition with observables, which can be very practical for doing some more complicated observables. Yeah, you already heard a bit by Emily about the Wick decomposition and the talks about observables. We will also hear a bit more about this. Then here, second part of the ALF of the folder structure. In the analysis folder, there are error analysis programs. If you use PyAlf, you won't need those, but without PyAlf, there are here these folders to do the error analysis of the finished Monte Carlo run. Then in the HDF5 file folder, this is also a folder you usually don't have to worry about. It's just this folder. It's automatically ALF automatically downloads and compiles HD5, and there it will be placed. So this is also the reason why the first time you compile with HD5, it will take a long time, because ALF will itself download and compile HD5. Yeah, libraries are some general routines. For example, the lattice. This is also for most users not so interesting. And in the proc folder, there is all the kind of the most interesting part, because there is all the Monte Carlo stuff is happening in there. And then there are two other files which are very relevant. This is the configure file, which is must be sourced before compilation to set the environment variables the compilers need. And then the make file is that make, what is the way we use what we use for compilation. Yeah. And then here's finally the folder proc, which is as I said, the folder which contains all the Monte Carlo stuff. And here the most interesting things is the Hamiltonians.list is so the list of Hamiltonians that ALF compiles and includes in one executable. And you can also use the Hamiltonians list.d. Basically, the files that are in Hamiltonians list.d will just be appended to Hamiltonians.list dynamically. And this Hamiltonian main is the interface between Hamiltonians and the Monte Carlo code. So basically, like as most users only, if they have to touch some Fortran code, they basically only have to use Hamiltonians. And this one file is basically that's a translation layer between the Monte Carlo core and the user side, so to say. And then in this Hamiltonians folder, you have all the Hamiltonians, which are submodule of this Hamiltonian main. And in main.f90 is the main program. So basically, that's when the code is executed. Main.f90 is where everything starts, and main.f90 then calls everything else that's needed to do the Monte Carlo code. And alf.out is the executable, which most of you already have executed to run Monte Carlo, or all of you ideally. Yeah, and here are the things people have to touch if they want to implement a new Hamiltonian. So basically, they have to create a new a new submodule which defines their Hamiltonian and then add this to the list. So either append it to this file or just add a new file here in this directory. Yeah, and this is the way how the interface between the Monte Carlo part, like the Monte Carlo core, I call it, and the Hamiltonians work. So basically at the very start, this ham name is read from the parameter file, and then depending on what's written in there, the according Hamiltonian gets allocated. So for example, the Hubbard Hamiltonian, Kondo, or yeah, whatever you're interested you are, for example, TV model or so. And now I will take a quick peek into the Hamiltonian main.mod, which, as I said, is this defines this interface between the Hamiltonians and the part most users don't have to worry about. So basically, here is everything defined that users can use to interface their Hamiltonian with the main part. So for example, like the most important thing is this ham set, which is one subroutine that gets called at the very beginning that defines all that defines the Hamiltonian. So that's the hopping and interaction matrices. And then there are a lot of other things which are by default set to some base types, which you can see here. So if you want to implement a more exotic Hamiltonian, it might be worth to look into this file and see what kind of ways you have to interface this Hamiltonian with the with ALF basically, and then can look at the base versions of these subroutines or functions depending on what you look at, and adapt them to your needs. Yeah, that's what I wanted to talk about, the Hamiltonian main module. And now the last part is just to look at the main file, so basically which is all the steps that get executed in a bird's eye view in the doing the Monte Carlo things. Yeah, doing the Monte Carlo simulation. So yeah, the first step is that all the Monte Carlo parameters I get read from the parameters file. Then depending on which Hamiltonian name is written in the parameters file, one of the Hamiltonians is chosen. And then this user-defined subroutine ham set is called, that defines all the model like the model. Yeah, it defines the model. And then the auxiliary field configuration either gets read in or generated Hamiltonian generated randomly. And this is, yeah, always a caveat that you can't mention often enough for beginners, I think, is that basically, so after one simulation, ALF will, or after each bin actually, ALF will produce these checkpoint files, which are called conf out, and then from 0 to some number of MPI processes -1. So basically for each MPI process, one of these conf out files. And the user has to manually rename these to conf in if you want to restart a simulation, and then ALF will read these files. Otherwise, if the user won't do this, the previous simulation will just be repeated, and then you have 2 times the the same bins. Then what is then done is basically some bookkeeping is done basically mainly for the stabilization, which is not so important, I guess, for the beginner. And here is so that's the main meat. So we have two big loops, one over the number of bins, and then the other over the number of sweeps. This was already also a question that has been basically addressed previously. So that basically you have some number of bins, and for each number of bin, you do n. For each bin, you do n sweeps, and each sweep starts with, if you have parallel tempering enabled with exchange steps, then you can do a global update. If you have global update enabled, then the lingerie update is executed, and then you sweep. You do all the sequential updates, which Johannes explained. So you sweep up, like touch all fields once, and then sweep down and touch all this spins once, and then you then all the time displaced observables are measured, and yeah, this is done for n sweep times. After this, all the current measurements are written to disk, which constitutes one bin, and the current state of the auxiliary field configuration and also the random number generator is written to disk, which are these conf out files. And then, yeah, what I will do now is look at what exactly happens during one sweep up. This is namely this thing. So first, you basically do propagate the Green function from one to one new time slice. So basically, each for one imaginary time slice, all the spins, like a single spin flip update, is done for each space point you have. And then if the last stabilization was nrep time steps away, then you are the next stabilization point, and then the stabilization step is executed, and there's measured whether the Green function is precise enough, and it's not too precise enough. Then if it's very imprecise, the code will abort, and then for each of these time slices, you measure once the equal time observables. Yeah, this observ t somewhere is here wrong, because like observ t is called for once per no, not once, but multiple times here for the time displaced observables, but this tau m is yeah, measured outside of the sweeps basically. Yeah, and that's basically this bird's eye overview over the folder structure and the code. So thank you for your attention for this part. Are there any questions?
Questions from the audience? Yes, Maxime. Oh, sorry, I was not.
Maybe
getting
maybe
warm.
I didn't get it, but in which folder is its file main F90?
Yeah, it's in the proc folder. It's in the proc folder. Yeah, here. Sorry.
Hamiltonians and then.
So here in the proc folder, there's the Hamiltonians.lib.
Yes, I'm there.
And also the main.f90 is here in the proc folder.
More questions?
Okay, fine.
Did you find it?
There are not so many files which almost have the same.
Yeah, try to make clean, and then you have a bit more overview.
Yeah, if you don't clean things up, you'll get lost.
Can I have a question?
Sure,
course.
please go ahead.
So if I understand, you do one sweep up, other sweep down, and then you measure observables, right? I mean,
No, once the time displaced observables are then measured, the equal time observables are measured after every time slice.
Oh.
So,
Mhm.
sorry.
So normally you have to
here.
be very careful. Normally
ba-
it's not so expensive to measure equal time observables. So you can measure them often, normally, right? So that's why that's a default. Energy, for example, is order n, where n is the number of sites. So you don't really care about that.
Okay, so you can measure the equal time observables after every time step because you already updated all the system.
Yeah, so you have
So-
the equal time greens function at the end of you update, as Johannes said, you update one time slice, right?
Mhm.
And then at the end of the time slice, you can calculate, you have the equal time greens function, and with this quantity, you can calculate any equal time observable. And you
Okay,
do it, right?
okay, thank you.
You're welcome. Yes, please. Here you go.
So if I write a new Hamiltonian, so would I have to write all the steps like some Langevin update and all, like, or is the
No,
basic-
no. That's the nice thing about that. You basically only have to replace the things. So
Yeah,
so
maybe
basically, like you have to replace. So basically, these things, like you have to write some subroutine that that defines your hopping and your interaction matrices, and then you define some observables, and that's basically everything you need for a minimal thing. If you want to do some Langevin updates, then you have to, yeah. Somewhere here is also the
I think
So I
Jonas
think-
wants to say something.
Yeah.
Johannes, sorry.
So as a comment to this, so if you look, for example, at these file function names, there is a global move tau. There should somewhere be global move. There is an override global tau sampling parameters. So whenever there is something in the name similar to Langevin that indicates that you are using a higher level updating scheme that goes beyond sequential spin flips, these are typically optional. So if you select in your parameters file that you want to do global moves, then you should also provide the global move function, which defines how do the moves look like. If you don't choose the global moves, then it doesn't matter if this function is there or not, or if you overwritten the default value. And we paid attention that the routines should tell you, this is a routine that is missing and I don't know what to do. And then the code will crash and tell you this function has not been implemented.
Well, it will tell you, it won't crash.
It
will
won't
tell
write it for
politely,
you.
but
well,
at
in
least
some
provide the
in
routine.
some cases it will crash. Like it will abort.
It will also
but
tell you, for example, when you think of the global moves, you need a routine that calculates the global change of S naught for a global move. But you can reconstruct the global change of S naught by doing virtually single spin flips, by reconstructing the cluster through single spin flips. So in some cases, there are fallback routines which can do the job, but maybe not efficient. And then the code will run, but it will tell you that it's using an inefficient way of doing things. In another case, that it tells you, I don't know what to do, please help me out.
yeah, I mean, if you look at this file, if you're interested in this, but in principle, like if you want to just do some, like for most models, if you do not do some very intensive work, the single spin flip update is anyway the most effective, I would say. And then you just have to basically, like if you define those three, then you already have a working simulation. Yeah. But you will also, like on Wednesday, there will be like a summary where we will explicitly see how to build a new Hamiltonian. Sorry. We also have like a template file which you can just copy, and then it says where to fill in stuff to get a working Hamiltonian.
More questions, comments?